Let us discuss problem number 44 of 200 puzzling problems in physics. What we are given is we have a plate that is bent at right angles as shown. This is a right angle, and that is placed on a fixed cylinder of radius r as shown in the figure. This is a cylinder, and we have to tell the range of coefficient of static friction between this cylinder and this plate so that the plate does not slip off the cylinder. Okay, so what we do is we draw the forces that are acting on the plate, and we have to do translational equilibrium and rotational equilibrium. We write equations and then solve those equations. What is beauty in this problem is, right, it is normal that we write the equations, we do these things in other problems, but how we solve those equations, how we manipulate, that mathematical point of view is quite important in this problem. So let us start. Okay, so this is my arrangement in which this is cylinder and this is the plate as seen out here. So what we do is, firstly, we are not given the mass of the plate, so we assume the let mass of plate is equal to 2m. We assume it to be 2m because then this side has mass m and this has mass m because these are identical. So we draw the forces acting on this plate. Okay, firstly, there is a force mg acting at this point, a force normal, let us say it to be n1. This is the force on the plate by this cylinder. Okay, it is, we are drawing the forces on the plate. Okay, and here there is friction on the plate. Let us assume to be in this direction, right? I can see by qualitatively I can tell it has a tendency to rotate like that, so friction will be acting in this direction, or you can assume it to be in another direction. After that, finally you will get that correct answer, you will get friction negative. Okay, I assume it to be F1. Okay, these are the forces acting on this side of the plate. Now what are the forces on this side of the plate? Again, a downward force mg acting at the center of this plate, and then we have a force n2 in that direction and a frictional force in that direction. Let us say it to be F2, right? So what we have is, now we write equilibrium equations. Okay, firstly what I can say is I can balance the vertical forces. Vertical forces are n1 plus f2 would equal to mg, 2mg because mass is 2m, and f1 equal to n2. Okay, and now balancing torques. Suppose I balance the torques about this point O, because then frictional torque would cancel out, right? Cancel out in the sense they would become 0. So what I have is, let us suppose the cylinder has a radius r. What I have is mg plus n2r is equal to n1r. This one mg, this f2 and this f1, they have torque 0 about point O. So this would be the equation, that is mg plus n2 equals n1, right? And we also have two inequalities, that is the limiting values of friction. F1 would be less than equal to mu n1 and F2 would be less than equal to mu n2. Okay, now we have to use these equations, this equation number 1, this equation number 2, this equation number 3. let us see what we can conclude from these three equations. See, from this equation number 2 and equation number 3, I can clearly write out mg plus f1 equals n1. Let us name it equation number 4. What I do is now add equation number 1 and 4. So what I would get is n1 would cancel out from this n1 and m from that mg. So basically I would get f1 plus f2 equals mg, right? This equation. And secondly, I know that n2 is equal to f1. Okay, I can substitute it in this. f2 is less than equal to mu n2. This implies I would get f2 is less than equal to mu f1, right? And then what I have is f1 is less than equal to mu n1, and I can substitute n1 from here. N1 is equal to mg plus n2. So what I would get is f1 is less than equal to mu times mg plus n2, and n2 is basically, from here I have n2 is equal to f1. So substituting it here, I would get f1 is less than equal to mu times mg plus f1. This implies f1 is less than equal to mu mg upon 1 minus mu, right? And surely we are assuming that mu is less than 1. Okay, now what the task is, we get some inequalities. Using these inequalities, we have to tell the possible values of mu. Now the problem says what are the possible values of mu that we have to tell. So what we do is, that is a very smart work. You have to remember that this in future, that we have three inequalities, and we have inequalities in terms of f1 and f2. Here f2, f1, here f1 we have a range, and here we have f1 plus f2 equal to mg, that is sort of x plus y equal to some constant, right? So what we can do is, we can plot a curve. Shortly between f2 versus f1, where we have taken f2 on the y-axis and f1 on the x-axis. Shortly then what we would have is f1 is less than equal to this value. So I draw a line parallel to y-axis, something like that, where this point, that means this distance, is mu mg upon 1 minus mu, and f1 is less than equal to this value. That means I have this region on the left side of this. Then I have f1 plus f2 equal to mg. That would mean something like this. Right? This point is mg. Okay, this we have written mg, here we have written mg is greater than this. Okay, this is possible when mu is less than 1 by 2. So we name it to be case 1, when mu is less than 1 by 2. We will discuss another case after this. So, and again here this is also mg, right? And another what we have is f2 is less than equal to mu f1. Okay, f2 is less than equal to mu f1 would be something, it can be something like this, or it can be below this. We will discuss this case after this. Okay, So what we have, I shade the region of interest. We have this region, okay, we have this region, whole of this region. These intersect in this triangle, and then we have f1 plus f2 equals mg. That means this line. So we have these much possible values of mu. This from point A to B. These are the possible values of mu. So what we have is, we do not have a unique solution. We have a range of values. This is the case when mu is less than 1 by 2. And secondly, what we have assumed is that this point, intersection of f2 equals mu f1 with f1 equal to mu mg upon 1 minus mu, lies above the point of intersection of this. So what we can easily do is we can calculate the condition by assuming, by taking the case when this passes through this point only, point B, this line. Okay, so what we can write then is, we calculate point B and we put it in f2 equals to mu f1. Okay, we have to do a little calculation. We have f1 equal to this, and we would get f2 equal to mg minus f1, mu mg upon 1 minus mu. So basically what we would get is mg common, that would be 1 minus 2 mu upon 1 minus mu, right? And this comes out to f2, and we have f2 equals mu f1, that is mg mu into 1 minus 2 mu upon 1 minus mu is less than equal to mu square mg upon 1 minus mu. Mu mg would cancel out, mu mg cancels out, 1 minus mu cancels out, right? So what we have is 3 mu greater than equal to 1. Oh, sorry, here there is no mu, so here comes mu square. Sorry, I did a mistake. Here comes mu square, because we have f2 equal to this, and we have f2 less than equal to mu f1. So basically mu square plus 2 mu minus 1 greater than equal to 0. And greater than equal to 0, we can take the equality when we are taking the limiting case, that is mu square minus 2 mu plus 2 mu minus 1 equal to 0, that is mu is equal to minus b plus, we are taking only positive root b square minus 4ac, that is 8 by 2, that is root 2 minus 1, that is approximately 0.414. This is the limiting case. In this situation, we have only this unique value, and mu is equal to 0.414, right? And this value, as we can see, is less than 0.5 shortly. So if mu is greater than this value, 0.414, then this point would lie above point B, right? So we have acceptable solutions as mu is greater than root 2 minus 1 and less than 1 by 2. Then mu lies between these values, and I can put equality here. I'll see equality at 1 by 2. When mu is this, then the disk can be at equilibrium, right? If mu is less than root 2 minus 1, then equilibrium can't be there, right? So mu has to be greater than equal to root 2 minus 1. That is the minimum value of mu, and we see how much on the upper side it can go, right? So we make another case when mu is greater than 1 by 2. In that case, what happens is this point switches to the right of this point. Okay, we make another graph for this. Okay, so for mu greater than 1 by 2, this is our curve. I explain you the curve. Just what we have done is that this point now has switched to the right of this point mg. This is the point where f1 plus f2 line, f1 plus f2 equal to mg, intersects the f1 axis, right? As we can see in the case mu greater than 1 by 2, we have acceptable values. Mu can be greater than 1 by 2, as this is the region of interest. Now, rather I would say this region is our interest, because we need f1 f2 less than equal to mu f1, that is this region, and f1 less than equal to this value, that is this region, right? So we have this whole area, this segment. What happens now is f2 can be negative. As we have discussed earlier, we had assumed the direction of f2 to be towards left side, right? As you can see here, we have assumed f2 to be upwards. Now f2 can be negative, f2 can be downwards, and this is the case when mu is greater than 1 by 2. f2 can take negative values. That is just the direction. Okay, so mu greater than 1 by 2 is also acceptable, and rather I should say here mu greater than equal to 1 by 2, because if mu is equal to 1 by 2, this line would just pass through this point, and then again we have possible values, right, of f2 and f1, right? So what we get is we get a lower bound for mu. Mu should be greater than equal to root 2 minus 1 for the given situation to be possible, right? So this is our problem, and this is a detailed analysis of this problem. So what we did basically is nothing but we wrote the equations, translational equilibrium equations, rotational equilibrium equations, and we solved the problem using graphical inequalities. That is the case that we have to discuss, and we must remember it in the future also, because this shortens the problem. Otherwise, if you have solved this with solving the equations, putting values from one equation to another equation, solving variables, that would be a quite tedious and lengthy task, right? Here we can see easily by inequalities. Okay, then we just end up, and thank you.